Welcome to this lecture series in real analysis. In this lecture, we'll see how the notions of limits and continuity are connected. This shouldn't be a surprise. The formal definitions for both of them are via the epsilon delta criterion. So clearly there is a connection, but here we'll just solidify that connection. All right. Here are some problems for practice. And now let us get started. So here is the theorem. Suppose f is a function from a subset S of reals to reals, and x0 is a point in S. So I'm not saying that x0 is an arbitrary real number, it is a point in the domain, very important. And also assume that it is an accumulation point of S. Then the following two statements are equivalent. The first is that the function is continuous at that point, and to even talk about continuity of the function at that point better be in the domain. Otherwise, how can you even talk about the continuity of the function at that point? So this is statement 1, and we are saying that it is equivalent to saying that this limit exists and is equal to f of x0. So this is our first statement, and this is a very simple exercise really, but let me prove it in full. So first we'll prove 1 implies 2. For that, assume that 1 holds and let epsilon be greater than 0. Then by 1, there is some delta greater than 0 such that whenever you choose x in this delta neighborhood and in the domain, you choose x in the delta neighborhood of x0 and in the domain, of course, then the function respects the value at x0 with the tolerance of epsilon. So immediately using the fact or the definition or the epsilon delta criterion of continuity at the point x0. Okay, but this tautologically implies that, let me not use too many implies signs. So this gives, if you choose x in S and x in this delta neighborhood and different from x0. So now you're choosing basically in the delta deleted neighborhood of x0 and in the domain as well. So that implies the same thing as the previous one. If this is true, this is clearly true, tautologically. Not tautologically, but maybe, immediately. Here, you have just relaxed, or not relaxed, but whatever was the conditions here, you have a subset of those conditions in down below. You're just dropping one more thing. So anyway, this implies that should be clear to you. And that implies that 2 holds, that limit exists and is equal to fx0. Thus, so this is trivial, and this other direction is also equally easy, but let me do it. So here again, let epsilon greater than 0, and by 2, we know some delta positive such that whenever you choose x in the domain and in the delta deleted neighborhood, you get this inequality. Oh God. You get this inequality, and this immediately implies that implication. Why? Because this is true. Okay, how shall I say it? This we have just by 2, but even at x equals x0, this equation is clearly true. At x equals x0, this is 0, and hence this is clearly true. So we may as well erase this. We may as well drop this special insistence, and still this implication holds. And if this implication holds, then we have found a delta responding to this epsilon, and hence 1 holds. Therefore 1 holds. And we are done. So this was a really simple exercise. Okay. Now for the interesting part. Equally easy but interesting. So you have a function from a subset S of reals to reals. And this time we have an accumulation point of the domain, but we are not insisting that this is lying in the domain. This is just some point in the reals. It is an accumulation point of the domain. That is what we are assuming. And assume that this limit exists and is equal to some number L, some real number L. Okay? So since it is an accumulation point of the domain, we can talk about this thing. Before that, we can't even talk about it. And we are insisting that this limit exists and is equal to that. Then you define this new function f tilde on this set. X naught could have been a member of S or could not have been a member of S, doesn't matter. If it is already there in S, then this set is S. Otherwise, this is a set which is bigger than S. It has an extra point. Okay, so how is f tilde defined? You feed X to it. If X is different from X naught, you output f of X. If X is equal to X naught, you output L. So it's a new function. And maybe let's see a pictorial way to look at f tilde. Suppose my S is all of real numbers. And X naught is this point. Let me mark that. This is X naught. And the value at X naught is this guy. Now, if this is the graph of f, what is the graph of f tilde? Well, if you're different from X naught, you mimic the function f. So that mimicry is clear. But at the point X naught, f tilde takes the value equal to the limit of the function, which in this case does exist. What is the limit of f as x goes to X naught? It is this value. And that's what we see here. So there was sort of a defect in this function, meaning at X naught suddenly the function just flied off. This f tilde attempts to fix that defect, if there is a defect. Right, so I hope that motivates f tilde. And let's just prove that f tilde is continuous at the point X naught. Not that x tilde is continuous everywhere. F tilde is continuous everywhere. We are not claiming that. We are just saying that f tilde is continuous at X naught. Okay, so why is that? I don't want to take an extra page for it. So let me try to argue here, but that might not be sufficient. Let me try to argue here itself. So it's a brave attempt I'm going to make. So let epsilon greater than 0. We want to show f tilde is continuous at X naught. So since we have this limit, this is equal to L, we have delta greater than 0 such that if X is in the domain of the function, X is different from X naught, and it is in this delta deleted neighborhood. Yeah, so X is in the domain, it is in the delta neighborhood, but different from X naught. Is same as saying X is in the delta deleted neighborhood of X naught and in the domain. Then we have that these two things, fx and f of X naught, are not very far apart. They are epsilon apart at most. We have that. But note that I can just put a tilde here. I can just put a tilde because before, yeah. So here I can easily put a tilde, right? Sorry, what have I written? This is L. Sorry. This is L. Since this limit is equal to L, we have a delta. Given an epsilon, we have a delta such that this implication happens immediately from the definition of limit. or the epsilon delta way of looking at limits. Now, instead of fx, I can easily write f tilde x, because when x is not equal to x naught, you can write an f tilde here. F tilde x equals fx. That's the definition of f tilde. So there is nothing wrong with it. And instead of L, I will write f tilde of x naught, because f tilde of x naught is L by definition. Okay, so we have this. But what happens at x equals to x naught? If you have x equals to x naught, this is obviously 0. So I can also delete this, right? So clearly there is a delta which witnesses that the epsilon delta criterion for the continuity of f tilde at the point x naught holds. So this proves the continuity of f tilde. So we did not have to go to any extra page. Okay. Wonderful. And the converse is also true. I haven't written the converse, but if you define f tilde that way and it turns out to be continuous, then this limit is equal to L. So that part is also true. Just a reverse of this. So fine. I mean, yeah. And as an exercise, you can try and prove, or try to prove these things. Formulate and prove the one-sided versions of the things discussed today, of the theorems discussed today. Okay, so that's an exercise. And yeah, with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.